Hello, welcome to this video on Introduction to Adjoint Sensitivity Analysis. I will try in this video to give you an overview of the different adjoint sensitivity analysis techniques. It's a very short introduction, and you have to do lots of other reading to be able to implement your own codes. But hopefully you'll get the idea from these slides. And I will be discussing three main topics in this video: adjoint sensitivity analysis of circuits, adjoint sensitivity analysis in the frequency domain, and adjoint sensitivity analysis in the time domain. The sources I use in this video are two books. This is the first book here. This book it's a general optimization book, and chapter 10 is dedicated to adjoint sensitivity analysis. And I try in this chapter to give just a crash introduction and with some examples. So I would say it's very suitable as an introductory reading. And for those who want to read more about the subject, can go to the next reference. So this is the second reference. This is more dedicated to adjoint sensitivity analysis in the time domain, and we show in it how you can do sensitivity analysis for structures that have nonlinear materials, dispersive materials, anisotropic, isotropic, and this work was published in 2017. So if you find these videos useful, you may consider giving a reference to these two books, or try to read more into these two books to know more about the background of these different techniques. Okay, so now we start to ask why adjoint sensitivity analysis. The general optimization problem. This slide here talks about high frequency, but the concept is really the same, whether it's low frequency or high frequency. You have an electromagnetic structure. This electromagnetic structure can be an antenna or can be a electric motor. You have the parameters, the set of parameters X that determines the response, different dimensions, different material properties, and every time you give one set of these parameters to the simulator will give you the electromagnetic response. The electromagnetic response could be S parameters in high frequency, or it could be the torque and its rebels and the average torque and so on in low frequency motor analysis. Our target is to determine the optimal value of the parameters that will minimize the given objective function. Objective function here is f, and the objective function can have an explicit dependence on the parameters, or can have implicit dependence through the response. So this is really the general engineering design problem, and our target is to solve this problem with the minimum possible cost. How do we solve this problem? Usually we have an optimization code. We call this the optimizer. We give it the initial set of parameters. We give it the specifications. We use the specifications either to build the objective function or to use them as constraints. The optimizer will keep on calling the simulator and using the response it's gonna get, and the sensitivity is gonna get of the response is gonna do a number of iterations that will eventually give us the optimal response X star. Okay, so this is repeated. These steps here are repeated a number of times until we move from X of 0 to the best possible estimate of the optimal solution. The problem is gradient-based optimization that requires sensitivities, requires derivatives, will require also the gradient of the response. And the gradient of the response, as you have seen in my optimization course or other courses, would require using finite differences to estimate the sensitivities. And the cheapest finite difference approach is the forward finite difference or backward finite difference. And this will require n extra simulations. So the original simulation and n extra simulations. Central finite difference would require 2n extra simulations per one gradient evaluation. So this cost can be big if one simulation takes a long time, or your number of parameters here, the cardinality of x is huge, the order of x is huge. So there must be another way of to be able to obtain the gradient in a more efficient way. So the basic idea of adjoint method is to solve the original structure that you have, the motor or the antenna, with the parameters x to get the response, and then build another structure, another motor. You can call it this way, another antenna, and give it the same parameters x. You're gonna get something called the adjoint response. Using R and R hat, evaluate the gradient, all the components of the gradient, all the derivatives of the objective function relative to all the parameters, this is with respect to all parameters, regardless of n, are obtained. So here we needed only one extra simulation, and so the extra cost that we have here is 1, is not really n. You do only one adjoint simulation, which has the same cost as the original simulation. And so this reduces the cost of obtaining the gradient, which is partial f partial xi for all I, where xi are our parameters, from n to 1. You reduce the cost from n to 1. And if you read in my book, in 2 books about the subject, you will know that you can even reduce the cost to 0. You can make the cost go down, the cost of calculating the gradient go down from n to 0. So you don't really require even the adjoint simulation. Sometimes we can get rid of it. This will depend on the objective function f. This approach started in the area of electrical engineering in the 1960s, and there are some early publications that talk about that, and you find reference to these publications in my book, in my 2 books actually. But the main focus of my work in this area was on applying this to electromagnetic structures. The first part in these videos will focus on getting the sensitivity of voltages in an electric circuit or currents in an electric circuit relative to all the parameters of the electric circuit. When I say parameter, I mean the value of this resistance, or if you have capacitances, how do you get the sensitivity of the response relative to all the components? Okay, so I can get maybe sensitivity of this voltage, maybe I can get the sensitivity of this current. How do I do these calculations relative to all the parameters? Even if you have a circuit with 1 million parameter, how you can get these sensitivities? So the base here, the starting point of this point is Telegraph theorem. Telegraph theorem is an extension of the conservation of power. We know that you have an electric circuit like this one, then the sum of power of all branches is going to give you 0. But we talk about the circuit, so for example, if we talk about this V1, positive, negative, then the current I1 will be flowing this way. V2, positive, negative, the current I2 will be flowing this way. This is V3 here, it's between this point and this point. Then the current I3 will be flowing this way. If we sum VI, the voltage in every branch multiplied by the current in each branch, we are going to get 0. Okay, but of course, as I said, the current has to be flowing from positive to negative through the branch. Now, this theory can be extended to 2 different circuits. So here we have one circuit and a second circuit. What makes these 2 circuits, what the connection between these 2 circuits is given by the fact that they both have 2 nodes, like this one here, and they have 3 branches. Okay, so they have the same topology, you can call it that way, the same graph, you can call it that way. So if we find the voltage in the first circuit and the corresponding currents in the second circuit, so this is I1, this is this I can call this one I1 hat, this is V1, this one is I2 hat, this is V2, this is I3 hat, this is V3. So I pick the branches, the voltages from one circuit and the currents from the other circuit. If you sum the product of these voltages and currents over all the branches, you are going to get 0, which is really a surprising result. So even though the 2 circuits can have completely different components in their branches, but as long as they have the same number of nodes and the same number of branches with the same graph, actually, the same graph. Here 2 nodes, 3 branches, here 2 nodes, 3 branches. You are gonna get that the sum of products of VI, you multiply every voltage in the first circuit by the corresponding current in the second circuit, and you sum over all branches, you are gonna get 0. This result is really whatever, is very interesting result, and this is the result they used to get sensitivity analysis of circuits. Okay, I'm not gonna be giving the complete details because it's pretty lengthy, but I will try to show you the basic result, the main result, of a long derivation. You can find this derivation in my first book on optimization, and it can be found in many other references. And I give detailed reference to all these work that you can find useful. There aren't really many in the 60s and 70s, but the few ones that I could put my hand on, I gave reference to them. Okay, so we start by writing the system of equations relating the currents and voltages in the branches to one another. Here we divided the branches in the first circuit into 2 sets, set A and set B. So the currents in the first set of branches called IA, the voltage in the first set of branches called VA, the voltage in the second set of branches called VB, the current in the second set of branches called IB. Okay, so we did some sort of division of the branches. This division or this notation allows us to handle things like transformers, like transmission lines. We can include them in this derivation. You write how every current is related to the voltages, and you can see that the current in one branch, for example here, can be related to the current in another branch. So you have a current dependent current source as well, or something like this. You can see that the voltage in the branches B can be related through the matrix M to the voltages in branches A. So this can be used to handle a voltage dependent voltage source and so on. If you can write your system in this form, then the theory, which you can find detailed derivation of it in my books and other references, the corresponding adjoint system is given by this form. The corresponding adjoint system is simply you take the transpose of 2 matrices in the diagonal, and you invert the 2 matrices in the off diagonal, and you take the transpose with a negative sign. So this is how we get this system. This is called the adjoint system. So the adjoint system tells you that the current in set of branches A in the adjoint system is given as this product with the voltages and currents in the adjoint system of voltages of set A and currents of set B. Okay, this will become clearer later, but just keep in mind that we divided our branches in the original circuit into 2 sets, set A and set B. And then we wrote the expression or the matrix related the currents in set A and the voltage in set B to the voltage in set A and the currents in set B. Okay, and then we found this given by this matrix form, and then if you can write in this matrix form, then the adjoint system is given by this one here. So one thing to notice, if this describes a circuit, this also describes a circuit, and this is called the adjoint circuit. Now if you manage to solve this circuit here, and you know the currents and voltages everywhere, and if you manage to solve this system here, and you know the currents and voltages everywhere in the adjoint system, then this expression will hold. Again, there is a long derivation for this. I'm not showing it in these slides. What this expression is saying is that if you want to get the derivative of a certain current, the kth current in the original circuit, relative to any one of your circuit components, xi here could be a resistor value, could be an inductance value, could be a capacitance value, okay, then you multiply this sensitivity, this desired sensitivity is multiplied by the voltage across the same branch in the adjoint circuit. Remember, the adjoint circuit does not have to have the same components. So here you can have a resistor going through the kth branch, while here you can have a voltage source of value 1. So you can make this one equal to 1. Okay? So we can tailor the adjoint circuit such that only one of these VK hats and none of these IK hats are, only one of them is non-zero. So this means you are picking only one sensitivity, partial IK, partial XI. And you can do this for all XI. So let's imagine this what we have. You gave this one of these one of these VKs, and we are summing over all of them, over all voltage sources. You give it 1, then you pick the only one sensitivity relative to XI. The interesting part on this in the other side, really this is very interesting. These are the voltages and currents of the original circuit. These are the voltages and currents of the adjoint circuit, and these are the analytical derivatives of this matrix that we have here. Okay, that we have here relative to the parameter xi. But we know these matrices analytically. We know them. We don't have to calculate them through finite differences. So what is this saying is, regardless of xi, you can take x1, x2, x3, x4, x1 million. You need only two simulations: the voltages and currents in the original circuit, voltages and currents in the adjoint circuit, and this matrix is known analytically for all xi. This is what this is saying. How do we use this formula? Well, you have to make only one of these VKs equal to 1 in the adjoint circuit. So this means you are getting sensitivity of the current in a certain branch. Or you can pick this current IK hat, one of them, only one of the IK currents, make it equal to 1 in the adjoint circuit. So you are picking only sensitivity of VK relative to all the parameters. We can do that. So we are the ones who set the adjoint excitation. I'm going to clarify this with an example. I know it's a little bit abstract right now, but when you see an example, you will realize how it works. Just remember, my target, if I want to get the sensitivity of the current going through one branch, I have to have a voltage source of value 1 in parallel to it in the adjoint circuit. And if I want to get the sensitivity of the voltage of a certain voltage in the original circuit, I have to put a current source of value 1 in parallel to it in the adjoint circuit. Okay? So remember, I have to make this equal to 1 here, and then I'm picking sensitivities I'm looking for. Okay, so these are the general steps. The steps are pretty straightforward. Solve the original circuits, calculate the currents and voltages in all branches. You have a circuit, you have the excitation for that circuit. Solve it using any of the methods we learned in circuit analysis. Get the solution. Build the adjoint circuit and determine excitation to select the derivatives of the response of interest. So we agreed that I have to go in one of the branches, I have to put a voltage source or a current source in the adjoint circuit, and this will have a value of 1. Okay, this is gonna select for you which derivatives you are looking for, the derivatives in this of a certain current or the derivative of a certain voltage. Now solve the adjoint circuit using this excitation that we've chosen and get the adjoint voltages and currents everywhere. Now for all the parameters xi, we can apply this formula. Okay, this formula, only one of these VKs will be 1. So we are picking only partial IK, partial XI for certain K and for all I. Okay, remember, we know these analytical sensitivities, we know them. We know the solution of the original system, original circuit. We know the solution of the adjoint circuit. So by doing so, you can really obtain your adjoint sensitivities. I can get the sensitivities of the current through a certain branch relative to all xi, relative to all your circuit components. Or if I put a current source of unity value, I get the sensitivity of the voltage across a certain branch relative to all your parameters. So, and I can use that, by the way, to get sensitivity of things like input impedance and so on, because these are byproducts of sensitivities of voltages and currents. Notice that one word of warning: these matrices are complex, because in general this is AC analysis. So you have to realize that these are not real matrices. This could be complex matrices if you have capacitors and inductors and so on. Okay, let's consider a simple example. We have here this circuit. It's a circuit with one source. Okay, we have this source here. We have one load and we have an RC branch. Okay. Our target is to evaluate the sensitivity of the output voltage V naught, which is a complex number relative to R and C and R1. So if I change R or C or R or RL of the load resistance here, V naught is gonna change. So I'd like to know what is the derivative of partial V naught, partial R, partial V naught, partial C, partial V naught, partial RL. In this case, our gradient has three components. Our target is to find these three components. We start by writing the governing equations of these branches. I have one branch here. They consider this as one branch. Second branch, third branch. Okay, we have three branches. I can relate the voltage across each branch to the current across each branch through this expression. Okay, so VR is equal to IR multiplying R. V, the voltage across the load resistor, is the current through the load resistor multiplying RL. The voltage across the capacitor is equal to the current through the capacitor multiplying ZC, and ZC is 1 over J omega C. Okay, this is, if you compare this one to the general form that we have, realize that we took only VB is equal to ZIB. Okay, so we have only here one set of branches, which is set B. VB is equal to ZIB. Because there is no Y, there is no current on the left hand side, it's only voltage is equal to impedance matrix multiplying current. This is what we have here. Voltage vector is equal to impedance matrix Z multiplying the current. So the matrices Y, A, and M are zeros. In some other application, may not be zero, okay? Then the adjoint system here will tell you, take the transpose of Z, and this will be your adjoint system. Remember, we don't have these matrices, and there is no IA, there is no VA. Then the adjoint system is VB hat is equal to Z transpose IB hat. It is exactly the same matrix, and this tells us that the adjoint circuit has exactly the same shape as the original circuit. Because this matrix here is diagonal, so it is symmetric, then its transpose it is equal to its value. Then the equation relating the currents and voltages in the adjoint system is VB hat is equal to Z transpose IB hat. VB hat, Z transpose IB hat. All the other matrices are zeros. Okay? Now, I want to get the sensitivity of V naught. Okay, then I have to make this V naught the voltage across a current source in the original circuit. This is what I have to do, because if you recall the summation that we had in the left hand side, it was talk about voltage sources and current sources. If you want to get the sensitivity of this V naught, I have to make this voltage the voltage across a current source in the original circuit. How do I do that? I have to come here and create an artificial current source of value 0 ampere. Okay, an artificial current source of value 0 ampere doesn't really change anything in the circuit because it's a source of zero value. Okay, but this will allow me to move in the adjoint circuit and put this source of value 1 to be able to calculate the sensitivities. Let's see how this is done in the next slide. So take a look at the trick that he had here. I would like to calculate the sensitivities of this voltage. So I created an artificial current source across it with this orientation here, with this direction here, of 0 ampere. It does not really change the original circuit in any way. But now V naught is the voltage across a current source. Then, as per the formula that I have given you, I can put this current here to be equal to 1 in the adjoint circuit. Okay, so I selected here ik hat to be equal to 1 for that specific branch. And now if I solve this circuit, I get the currents and voltages in the adjoint circuit. This is going to give me all the responses, all the voltages and currents of the adjoint circuit. So you can see this one has 0 ampere. It does not affect the original circuit. This one is the main source, has a value of 1. And you remember why I had to make it to be 1? Because I want to make the sensitivity of this voltage only, of this kth branch only. Okay, so I can make this one to be equal to 1. So now by solving these two circuits, I can get the sensitivity of V naught relative to RL, C, and R. All of them will come out as a result of this. So I wrote the formula here. This is exactly the formula that we have seen earlier. This is partial Vk partial Xi multiplying Ik hat, but Ik hat now is 1. Okay, so I picked one specific branch. This is a vector of original responses. This is a vector of adjoint responses, and this is the analytical matrix, the matrix with analytical derivatives that we talked about. Remember, we have here only Z. So this is partial Z partial Xi. Okay, and the Xi, by the way, here can be any one of the three components in the circuit. It could be R, it could be RL, it could be C. It could be any one of them. This is really the same formula that we wrote earlier. This negative sign, by the way, came from the fact that the summation that we have was saying a minus summation over all k partial Vk partial Xi multiplying Ik hat. So the negative sign here, I moved it to this side. Okay, so now we can move forward and calculate this. If I select Xi to be R, then this term will be 1 and these two terms will be 0. And this product will give me IR multiplying 1 multiplying IR hat. This is the current in the resistance R in the original circuit. This is the current in the resistance R in the adjoint circuit. So this is what we have here. So this is the first sensitivity. If I select Xi, if I want Xi to be RL, then this term will be 1. And because R and ZC are independent of RL, these two will be 0. 0 and 0. So the result that will come out of this row matrix vector column multiplication will be minus IRL multiplying 1 multiplying IRL hat. Okay, so remember when if I select Xi to be RL, only this component is 1, this is 0, this is 0. Okay, so if you multiply this row vector by this matrix, by this column vector, you'll obtain minus IRL multiplying 1 multiplying IRL hat. So the sensitivity is really the product of the two currents flowing through the resistance RL in the original circuit and in the adjoint circuit. For the capacitor is a little bit different. Why? Because if I select my parameter to be C, to be the capacitance, this is 1 over J omega C. Partial R partial C will give you 0. Partial RL partial C will give you 0. Partial 1 over J omega C partial C will give you minus 1 over J omega C squared. The derivative of 1 over X is minus 1 over X squared. The derivative of 1 over J omega C will give you minus 1 over J omega C squared. So this is 0, this is 0, this one here is minus 1 over J omega C squared. So if you multiply this row vector here, this is a row vector really because of the transpose, multiplying the matrix, multiplying the vector, this term will give me 0, this term will give me 0, this term will give me IC minus 1 over J omega C squared IC hat. And this is the derivative of V naught relative to C. Okay, so now what I did through calculating only the original response and the adjoint response, I was able to get the sensitivities of V naught relative to all the parameters. These matrices are available analytically. We did not really to do another simulation to get them. So if your circuit is huge, it took a huge amount of time to solve. You don't need to do that. Only solve the original responses, the adjoint responses, do this multiplication, they have all the sensitivities. So for the shown circuit, I'm showing you here the sensitivities relative to all the parameters. And of course, these sensitivities are going to be complex because V naught is a complex number. This is an AC circuit. And I did calculate the same sensitivities using central finite differences. Notice up to the fourth digit, you start to notice differences in the fourth digit. But other than that, they are almost identical. Maybe here in the third digit, but they are almost identical. This is a great thing. So the cost comparison, this one here, because we have 3 parameters, central finite differences would require 6 extra simulations. The adjoint method requires only 1 extra simulation. Okay, so as you could see, you can significantly reduce the cost of calculating the gradient. And this method, by the way, has been applied to techniques with tens of thousands or even millions of unknowns, of parameters. And we can get the sensitivities relative to all these parameters.